So this is the example problem for truss member. The truss consisting of two members. The length and the coordinates are given. One point load is applied at the midpoint. Now I am going to represent the nodal points. So I am going to take the node point 1 here, node point 1, and the coordinate x1, y1. Here the node point 2, so that the coordinate x2, y2. The node point 3, so the coordinate x3, y3. So the element number, this is the first element, this one is the second element. So we have completed the nodal numbering and the element numbering. This is one of the basic steps in finite element. So you can draw individually with the nodes and the elements 1, 2, 3. The element number 1, 2 with the coordinates x1, y1, x2, y2 and x3, y3. So now the coordinates x1, y1 I am keeping 0, 0, x2, y2. So this is the second node. So it is in the negative direction of x. So it is minus 500. And also it is in the line of 0th coordinate of y. So it is 0. Next one x3, y3. The third node. The x direction positive. The third node is in the positive direction. So plus 400. And in the y direction it is in negative coordinate. So minus 300. So we have completed the coordinate system. So the first thing, for the stiffness, forming stiffness matrix, we need L1, L2, M1 and M2. So this L1, M2 needs the effective length LE1 and LE2 for the members 1 and 2. So the LE1, effective length 1, is according to the coordinates of the node 1 and 2. So it is x2 minus x1 the whole square plus y2 minus y1 the whole square. For the element number 2, LE2, it is x3 minus x1 because the element number 2 connects the node 1 and 3. So it is x3 minus x1 the whole square plus y3 minus y1 the whole square. So this is the effective length for the element number 2. So now the cosine form for the first element L1, which is x2 minus x1 by LE1, which is x2 minus x1 by LE1, whereas L2 is x3 minus x1 by LE2. Similarly, M1 is sin theta, so y2 minus y1 by LE1. M2 is y3 minus y1 by LE2. So these are the parameters we are going to calculate now. So in next page I am going to write the coordinates again. x1, y1 is 0, 0. x2, y2 is minus 500, 0. x3, y3 is 400, minus 300, I think. Minus 300. So LE1 is equal to x2 minus x1. So minus 500 minus 0 the whole square plus y2 minus y1 is 0 minus 0 the whole square. So the effective length is 500 mm. LE2 is root of x3 minus x1. So 400 minus 0 the whole square plus y3 minus y1 minus 300 minus 0 the whole square. So it is root of 400 square plus 300 square root. It is also 500. It is also 500 mm. So now LE1 and LE2 is calculated. Next one, L1. L1 is equal to x2 minus x1 by LE1. So x2 minus x1 is minus 500 minus 0 by LE1 is 500. So minus 500 by 500 is minus 1. M1 is y2 minus y1. So 0 minus 0 by 500. So it is 0. L2 is 400 minus 0 by 500. 400 by 500 is 0.8 plus 0.8. M2 is minus 300 by 500 because y3 minus y1. y3 is minus 300, y1 is 0. So minus 300 by 500 is minus 0.6. Minus 0.6. So we obtained L1, M1, L2, M2. L1 is minus 1, M1 is 0, L2 is 0.8 plus 0.8, M2 is minus 0.6. So the next step is to assemble the element stiffness matrix. Element stiffness matrix. So we can name it as K1. K1 is A1 E1 by L1. I can write it as LE1. L1 square L1 M1 minus L1 square minus L1 M1. L1 M1 M1 square minus L1 M1 minus M1 square. So we have derived this equation in the previous video. Next one, the negative sign of the negative terms of the first row, minus L1 square minus L1 M1 plus L1 square plus L1 M1. The fourth row is the negative term of the second row, minus L1 M1 minus M1 square plus L1 M1 plus M1 square. So this is the terms we have to fill. So now we can write L1 square is minus 1 into minus 1 plus 1. L1 M1 is 0. Minus L1 square is minus 1 because L1 square is plus 1, but we have to put minus of L1 square, so it is minus 1. And also the Young's modulus is given as 70 gigapascal. So gigapascal, instead of gigapascal we can put 10 power 9 Pascal. Pascal means it is Newton per meter square. So we have to convert into mm square. So 70 into 10 power 9 into 10 power minus 6 Newton per mm square is the conversion. So ultimately we get 70 into 10 power 3 Newton per mm square. Area is given as 200 mm square. Area is 200 mm square. So LE1 we have 500 mm. LE1 we have calculated as 500 mm. So simply substitute in this 200 into 70 into 10 power 3 by 500. We can fill the value. L1 square is 10 minus 10. If you m is 0, no, so all the terms in the second row are 0. Next one, the negative component of the first row, minus 1 0 plus 1 0, and all the m is, since all the m value is 0, so the fourth row is also 0. So simply we have finished the stiffness matrix for the element number 1. So if you calculate 200 into 70 into 10 power 3 by 500, it is 28 into 10 power 3. 28 into 10 power 3. So we can write again 1 0 minus 1 0 0 0 0 0 minus 1 0 1 0 0 0 0 0. So we have finished one stiffness matrix for the first element. Next, stiffness matrix for element 2. Stiffness matrix for element 2. So it is K2. The area is not going to change. Young's modulus is also same, and also effective length also same. So you can write 28 into 10 power 3. Here you should change L2 square, L2M2 minus L2 square minus L2M2. L2M2 M2 square minus L2M2 minus M2 square, and the negative term of first row minus L2 square minus L2M2 L2 square L2M2. The fourth row is the negative term of second row minus L2M2 minus M2 square L2M2 and M2 square. So this is the required format for stiffness matrix. Now we can write L2. We know L2 is 0.8. L2 square is 0.64. L2 M2 is 0.8 into 0.6. Since M2 is negative, we can get 0.48. 0.6 into 0.8, it is 0.48. So negative sign for M2 value. And M2 square is 0.36 because 0.6 square is 0.36. With this value, we can fill this matrix. 28 into 10 power 3. L2 square 0.64. L2M2 minus 0.48 minus 6.64 plus 0.48, because minus L2M2 already minus value is there, so it is plus 0.48. Next one, minus 0.48, M2 square is 0.36, 0.48 minus 0.36. So the negative value of the first row, minus 0.64 plus 0.48 plus 0.64 minus 0.48, and the negative value of the second row, 0.48 minus 0.36 minus 0.48 plus 0.36. So we have completed the K2 matrix. So now we have to assemble the global stiffness matrix, for which it is called as global stiffness matrix, structure stiffness matrix. So different names are there. So I can write global stiffness matrix. So we can number this matrix. This element 2 stiffness matrix connects with 1 and 3 node. 1 and 3 node. So it has the displacement. So I am naming the displacement coordinate here as U1, U2, U3, U4 and U5, U6. So I am for the element number 2, it connects U1, U2, U5, U6. So I am going to name as U1, U2, U5, U6, or otherwise 1, 2, 5, 6. Simply we can specify as 1, 2, 5, 6. In the previous matrix, we can specify as 1, 2, 3, 4, 1, 2, 3, 4. Because if you are going to assemble the global stiffness matrix, you are going to see only the value 1, 1. Fill the value as 1. 2, 1. Fill the value as 2. 0. 3, 1. It is minus 1. In this manner only we are going to assemble the global stiffness matrix. The structure of the global stiffness matrix is going to be, so I am going to write So I am going to number this matrix 1, 2, 3, 4, 5 and 6. The column wise 1, 2, 3, 4, 5, 6. Our structure stiffness matrix should include all the nodal values, all the stiffness value of all the nodes. So it is from 1 to 6, column wise also 1 to 6. So in next page, we can write the two matrices for the element 1 and 2, because we need some hint to write 1 0 minus 1 0 or 0 0 0 0 minus 1 0 1 0 0 0 0 0. So the next matrix is 0.64 minus 0.48 0.64 plus 0.48 minus 0.48 0.36 plus 0.48 minus 0.36 minus 0.64 plus 0.48 minus 0.64. Sorry, I think it is minus here, because 0.64 minus 0.48 minus 0.64 plus 0.48. So it is plus. Here it is minus 0.48. Next one 0.48 minus 0.36 minus 0.48 plus 0.36. So with this using this matrices, we are going to assemble the global stiffness matrix. So K is equal to 28 into 10 power 3 is the common. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So first you need 1 value. So I am going to number here 1, 2, 3, 4. 1, 2, 3, 4. Similarly 1, 2, 3, 4 and 1, 2, 5, 6. 1, 2, 5, 6. 1, 2, 5, 6. So we have to get 1. It is 1. Here also 1 is available. So it is 0.64. So totally 1.64. We need 2 So it is 0. 2 is 0. Here it is minus 0.48. So simply minus 0.48. We need 3 1 is minus 1. There is no 3 here. So you directly put the value of 3 as minus 1. 4 is also available for only in the first matrix. So 0. 5 is available in the second matrix only. There is no value for first matrix. So it is minus 0.64. 6 is available only in the second matrix. So it is 0.48. Next one, we need 1 2. 1 2 is 0 here. 1 2 is 0 here. Here 1 2 is minus 0.48. So it is minus 0.48. Next one 2 2. 2 2 is 0 here. Here 2 2 is 0.36. 0.36. Next 3 2. 3 2 is also 0 here. So here no 3 2. So 0. 4 2. 4 2 is also 0. In the second matrix there is no 4 2. 5 2 is only available in the second matrix. It is 0.48. And 6 2 is available 0.36 minus 0.36. 1 3 is available in the first matrix. It is minus 1. 2 3 is available as 0. 3 3 is available as 1. 4 3 is available as 0. 5 3 is 0. 6 3 is 0, because there is no 5. There is no connection between 5 and third node. So here there is no phi 3 value. Here also there is no phi 3 value. Next one, 4, 1, 4 is 0. 2, 4 is 0. 3, 4 is 0. 4, 4 is also 0. 5, 4, there is no connection between 5 and the 4th node. So it is 0. 6, 4 also 0. Next 1, 5. So there is no element in first matrix. 1, 5 is available only in the second matrix. It is minus 0.64. That is 1 and 5. So minus 0.64. 2, 5, it is 0.48. There is no connection between 3 and 5, 0. 4 and 5, 0. 5 and 5 is available as 0.64. 6 and 5 is available as minus 0.48. 1 and 6, 1 with 6 is 0.48. 2 and 6 is minus 0.36. There is no connection between 3 and 6. So 0, 0. 5 to 6, it is minus 0.48. 6 to 6, it is 0.36. So we have completed the global stiffness matrix. Global stiffness matrix. So next I am going to formulate the equilibrium equation. Equilibrium equation. Equilibrium equation is equal to Ku equal to F. So K, I am going to again write 1.64 minus 0.48 minus 1, 0, minus 0.64, 0.48, minus 0.48, 0.36, 0, 0, 0.48, minus 0.36, minus 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, minus 0.64, 0.48, 0, 0, 0.64, minus 0.48, 0.48, minus 0.36, 0, 0, minus 0.48, 0.36. So this is our K matrix. Our displacement coordinate U1, U2, U3, U4, U5, U6, which is equal to, so look at the force component. There is only one force available in the node 2. There is only one force available in the node 2. There is no force in other nodes. So it is also in the vertical direction. So F2 is equal to minus 12. F2 equal to minus 12. So other forces are 0. Minus 12 into 10 power 3. Because of kilonewton, I am putting 10 power 3. Other load factors are 0. Now coming to the boundary condition, U1, U2 is available. U3, U4, 0. And U5, U6 is also 0 because of the fixed condition. So boundary conditions I am writing here. U3, U4, 0. And U5, U6 also 0 displacement. So we can neglect the corresponding rows and columns. So I am going to delete the row of U6, U5, U4 and U3. So I am striking the corresponding rows up to the force value. In vertically, this is the 6th column, 5th column, 4th column and 3rd column. Actually this finite element is very easy to calculate. Finally we are going to form only 2 by 2 matrix with the available boundary condition. So it is very easy to calculate. So I am going to consider only this 2 by 2 matrix with this unknown U1, U2 with this force component 0 and minus 12 into 10 power 3. So in next page I am going to write the consolidated matrix. So it is 1.64 minus 0.48 minus 0.48, 36 u1 u2 which is equal to 0 and minus 12 into 10 power 3. So we can write in the equation form 28 into 10 power 3 1.64 u1 minus 0.48 u2 is equal to 0. The next equation 28 into 10 power 3 minus 0.48 u1 plus 0.36 u2 which is equal to minus 12 into 10 power 3. So I am going to, I am keeping this is equation number 1, 2. I am going to multiply the equation 2 with a particular value to get 1.64 as the coefficient. The particular value 3.4167. If you multiply the second equation with 3.4167, you get 1.64 here, so that we can cancel the u1 terms. So I am going to rewrite this equation 1.64 u1 minus 0.48 u2 which is equal to 0. So I am bringing this 28 into 10 power 3 to the right side. So multiply, divide by 0 divided by 28 into 10 power 3 is 0. The second equation, if you multiply 3.416 into 0.48, it is minus 1.64 u1. Multiply 3.4167 into 0.36, it is plus 1.23 u2. And if you multiply 3.416 with 12, it is minus 41 into 10 power 3. So divided by 28 into 10 power 3, because I am bringing this 28 into 10 power 3 to the right side. So it is like this. So you can cancel this. And finally you get 0.75 u2 is equal to minus 41 into 10 power 3 divided by 28 into 10 power 3. So if you cancel, you can get minus 1.952 mm as u2. And if you substitute the u2 value in the first equation, you get u1 is equal to, I can write this equation first, 1.64 u1 minus 0.482 u2 equal to 0. So I am bringing this term to the right side. So 1.64 u1 is equal to 0.48 into minus 1.952. So u1 is equal to minus 0.5713 mm. So now the displacements are found out. Displacement u1 and u2 are found out. So next, the stresses in the elements. In the elements 1 and 2. Because the displacements can be found out in the nodes, the stresses can only find out in the elements. So first element number 1. Element number 1. So it is sigma 1. So we can write E by LE minus L minus M L1 M1 and L1 M1 M1 with the displacement coordinate of the element number 1 u2 u3 u4 u3 u4. So you know the value of Young's modulus 10 power 3 and the length 500. You know the value of L1 is minus 1, so minus into minus plus 1, 0, minus 1, 0. U1, U2 value no, minus 0.5713 minus 1.95200. If you multiply this, it is 1 into minus 0.713 because other terms are 0. So which is equal to 70 into 10 power 3, 1 into minus 0.5713 by 500, which is equal to minus 80 Newton per mm square. Similarly, sigma 2 for the element number 2. So I am going to directly write the equation for the element number 2. 70 into 10 power 3 by 500. L2 is minus 0.8. Minus L2 is minus 0.8 and plus 0.6 minus M2. and the negative of the first two, minus 0.6. And here we can write minus 0.5713 minus 1.952. U5, U6 are 0. So you can write 70 into 10 power 3 by 500 into minus 0.8 into minus 0.573. So 0.8 into 0.5713 minus 0.6 into 1.952. So which is equal to minus 100 Newton per mm square. So now the problem is over. The problem is asked to find out the displacement and stresses. So first the step is to fix the nodes and elements and fix the coordinates, find the length and find the cosine and sine term L1, M1, L2, M2 and formulate the element stiffness matrix, assemblage of global stiffness matrix and formulate the equilibrium equation, apply the boundary condition and neglect all the zero displacement rows and columns. Finally come with the matrix, net matrix and find the unknowns of displacement. Next you find the stresses. So these are the steps.